Welcome back on our broadcast. So now it's going to be exciting. So from initial mission requirements to flight operation simulation, Sylvain Lodiot from the European Space Agency is going to share his experience as the Hera Spacecraft Operation Manager, a position he already has on the Rosetta mission and the Solar Orbiter missions. So Sylvain, if he is here, you can join us. So a simple question for you. Is the video coming? Yeah, perfect. We have you. So simple question for you, Sylvain. How to operate a spacecraft from million kilometers away? So the floor is yours. You can go on.
Okay, thank you very much. Thank you for the nice introduction. I assume the slide presentation is going ahead, yeah?
Yeah.
Yes.
Okay, so
it should come in.
I'll be talking about the Hera mission. So next slide, please.
Yeah.
Please.
Yeah.
Perfect.
Yeah. Next slide. Okay, so the Hera mission is actually part of an international collaboration called AIDA. AIDA stands for Asteroid Impact and Deflection Assessment, and there's actually a fleet of spacecraft going to a binary asteroid. So the binaries are called Didymos and Dimorphos. The first part of the mission is actually a NASA part. It's called DART, which stands for Double Asteroid Redirection Test, which will be launched towards the end of this year. They have a launch window between November 21 and February 2022, with a DART impact in a few months later, September, October 2022. And the DART spacecraft carries the Lycia CubeSat, which will deploy roughly 2 days before impact. So the DART spacecraft is about 500 kilograms, and it will achieve the kinetic impact deflection by deliberately crashing itself into the moonlet at a speed of about 6.6 kilometers per second. And it has on board a camera which will allow it to do autonomous navigation towards its impact. The collision will change the speed of the moonlet by a little fraction, but that fraction would be enough, for example, to deflect an asteroid. For example, if you imagine a change of a speed of 1 millimeter per second, if you integrate this over time, then you would arrive at a proper distance, basically. Then comes the Hera mission. So the Hera mission will be, this is the ESA mission. It will be launched in October 24 with a 2-year cruise, and will arrive at the binary system in January 2027 for around 6 months of close observations of the binary. Next slide, please. So we actually already know a bit about the mainly Didymos. It's what we call a NEO, so it's a near-Earth object. You see the sizes here. So Didymane, which are called also Didymos, it's also called Didymane. It's about 800 meters wide. For the moon itself is about 170 meters wide. And this, you have here a picture of a comparison with the comet Churyumov-Gerasimenko, which was the comet of the Rosetta mission. So a NEO is an object which has its perihelion below 1.3 AU from the sun, which means that it potentially on one day could be on collision course with Earth. And because these orbits are fairly similar, so the Dimorphos goes between 1 and 2.3 AU from the sun, sometimes there are close encounters with Earth. For example, there was a close encounter in 2003 where already significant observations from ground could be made, and we'll talk about this a bit more. The asteroid was discovered in 1996 and had a number 65803 at the time. That was the number of asteroids we knew at that time. Of course, today we know many more. Its orbit is around about 2.11 years around the sun, and its rotation around itself is about 2 hours. And here you can see two pictures with the asteroids on the Earth's surface, both in Dubai and Paris. And one could easily imagine that an impact of such bodies on Earth would have catastrophic consequences. Next slide, please. So this is a close-up view of the Hera mission itself. So we're launching in October 24. We have a standard low and early orbit phase. So these are the first few hours of the mission in space. Then we'll have a commissioning phase of about 2 months, where we'll exercise and test all the payloads and the platform itself to make sure the spacecraft has survived the launch and is ready for the next phases. The cruise of 2 years will mainly be Mars swing-by. So we'll do a gravity assist of Mars. Basically, this is an exchange of angular momentum between the planet and the spacecraft. And this allows to change the speed and direction of the spacecraft around the sun, basically to better optimize the trajectory with the ones of the asteroids. We'll also have two what we call deep space maneuvers to even better tune the orbits of all these bodies and make sure that the encounter takes place. Once we arrive there, we'll have actually a few set of phases. So the first one will be an early characterization phase to basically understand where we are. We only know that system from ground today. Then we'll have a deployment phase where we'll deploy the 2 CubeSats we carry with us. We'll then have a detailed characterization phase with orbits between 8 and 20 kilometers from the surface of the asteroids for an accurate characterization of the moon and its physical properties. So here we're talking about 8 to 20 kilometers versus what Paul was saying just before. The spacecraft is millions, tens of millions, hundreds of millions away from Earth. Yeah, so how do we do this? We'll talk about this a bit later. Then we'll have a close observation phase going from 4 to 22 kilometers with high resolution mapping of the moon and the impact crater itself. This is very interesting scientifically. And then we'll enter the last phase of the mission with an experimental phase where we will try and go super close to the asteroids, mainly 1 kilometer, hopefully 1 kilometer, maybe lower, with also new technologies tested, so optical navigation and autonomous navigation from the asteroids fully on board versus doing it purely on ground. Next slide, please. So to be able to do this, we of course need a suite of payloads. Here you see the upper deck of the spacecraft with all the payloads on that spacecraft. So the first one is the asteroid framing camera, the AFC. It's actually 2 of them. We're taking images with them. This is in the visible wavelength with 8 filters. And those cameras will allow us basically to do optical navigation, both on ground or fully autonomously on board, using a technique we've already used on Rosetta, using maplets and features on the surface of the asteroid themselves. Then we have the thermal imager from JAXA, which is the Japanese agency. So here again, there's also a collaboration with Japan. We'll be doing radio science. So radio science is the utilization of the radio waves between the onboard antennas and the ground antennas using ranging and Doppler. And this allows to derive quite a lot of science, for example, the gravity, the mass of these bodies. Then we have Hyperscout. Hyperscout is a hyperspectral imager, and it's observing in 45 visible and near infrared spectral bands. Then we have an altimeter, which will allow basically which is actually a leader experiment, which will allow to determine the distance of the asteroids by measuring the time of flight of the laser beam. And last but not least, we have the 2 CubeSats, Juventus and Milani. So Juventus, among other payloads, will be carrying a low-frequency radar for subsurface sounding, as well as a gravimeter. And Milani will be dedicated to visual inspection of the moon and dust detection. So to be able to deploy these CubeSats, we need these deep space deployers, and to be able to talk to them once they're separated, we need what we call this ISL, this inter-satellite link. This will allow to talk to the CubeSats through the mother spacecraft back to ground. So there's no direct link CubeSats to ground straight. Next slide, please. So why going to asteroids? Why are asteroids so fascinating? There's actually 3 reasons for that. The first one is science, obviously. Yeah, so the asteroids are among the best traces of the history of our solar system. Yeah, we are all, as humans, try to better understand the solar system formation and where us human beings have managed to arrive on Earth. Then obviously the second main goal is planetary defense, validating deflection techniques and improving our modeling of impact crater generation. And then last but not least is resources. So everybody is fully aware that asteroids could be contain many resources which could, for example, help in future exploration of the solar system. So what is fascinating here is that with the same data, the same science data, we'll be able to reply to all these science goals. So as I was saying before, we know the system already from ground observations. So our ground telescopes, what they see is simply a point light source. It's just a point in the telescopes. But by looking at that point of light and seeing how the sun is reflected, it allows to get a lot of information already about this body. For example, the way this light is reflected gives a sign of the shape of Dimorphos. For example, if it's elongated or if it's a regular shape, and also the way the light gets periodical over time, and this gives the rotation of the asteroid itself. So from all these ground observations, the scientists have been able to deduce a lot of stuff about this binary system. For example, there's high knowledge and high accurate knowledge about Didymos, so the main body, orbit, size, spin, mass, and density. Yeah, whereas we know a bit less about its moon. Yeah, so this is known with more medium accuracy, and that's the whole point of getting there, to just be able to get all this knowledge. It's important to know as well that the Hera mission will be a first in many aspects. It's the first time we'll be rendezvousing with a binary asteroid. It will be the smallest asteroid ever visited. It's the first time we'll have detailed measurements of a crater created by a human being. It'll be the first time we deploy CubeSats and that they fly so close to asteroids. It's the first time we'll be able to see surface and subsurface information about the structure of asteroids, and the first time we'll attempt to land on the surface of an asteroid with the CubeSats. So next slide, please. So we've been talking a lot about science up to now. Let's talk a bit about operations, and this is actually my real job. So to be able to talk to the spacecraft, we need a network of stations, and we have our own station network, which is called S-Track, and we have 3 deep space antennas. They're 35-meter wide. The first one is in Ninosha, Australia. We have one in Cebreros, which is near Madrid in Spain, and we have one in Malagua in Argentina. We're actually building a 4th one in Ninosha, Australia. Next slide, please. So here you have a picture of the main control room in ESOC. This is where I work. The main control room is used for key events of a mission, typically the launch, but also key other milestones. For example, it's very likely that their CubeSat deployments will happen from this room. So right now the mission is ahead of us. And for a deep space mission, there's 2 key aspects. The first one is that we're not in permanent ground contact. Typically in cruise, we have 1 pass every week, and normal science will have maybe 1 pass per day of 8 to 10 hours. This means that the rest of the time, the spacecraft is alone on its own and has to be able to be fully autonomous. The other big step is what we call one-way light time. So one-way light time is a time the signal from the spacecraft comes to us, takes to arrive to us on ground, and on the other direction, the time we need to send a command and it reaches the spacecraft on board. And this depends on the speed of light. So for missions which are really far away, the one-way light time, or actually twice the signal travel time, can be in the order of tens of minutes. This means that we cannot do anything in real time. What we see from the spacecraft is always at least one-way light time old. And if you send a command to the spacecraft, it will execute later. Yeah, so we have to take all this into account for all our operations, which is mainly an offline exchange of data between the spacecraft and ground. Right now, we're preparing all the tools which will allow us to fly the mission. So this is all our control system, for example, or our planning tools. We're also preparing the concepts, so how we will operate the spacecraft. The concepts, we'll have to build up all the teams to be able to do this, and basically also we also need to document all what we'll be doing on the spacecraft. We call these procedures, flight control procedures. Everything we do on the spacecraft has to be documented and has to be validated on ground. Yeah, so this is what will be happening from now till launch. And then we'll be preparing, so the first 2 years of the mission and the rest, so the phases for the arrival at the asteroid and beyond, we will be preparing during cruise. So this is mainly it for operations. So the need of autonomy on board, big time. The spacecraft has what we call failure detection and isolation recovery. So it's able to identify failures and try to react to them. If it can't, then it will just raise a warning and let ground take over whenever ground is in contact with the spacecraft. On the planning, we once we're with the spacecraft in real life, there's different phases if you want. So there's the real interaction with the spacecraft. For example, in case there's a failure with the spacecraft or something to fix that, there will be the flight control team, so my team fixing that. But there's also all the planning aspects. So planning long term, so preparing for a phase which will be roughly 6 months down the road, and then bringing up preparing all the commands for our weekly cycle or bi-weekly cycle, so on a regular pattern. Yes, it's a cycle of planning on call. So I always have an engineer ready to react to whatever happens with the spacecraft, and then looking at the phases coming ahead and being ready to react to whatever comes to us. So this is roughly the working pattern once we fly the spacecraft. And before that is preparing to be ready to be able to do that. Next slide, please. So this is my last slide. It's a takeaway message for you guys. It's a quote I saw from an artist I saw in France. It was an exhibition, and this was a quote below one of his artwork, and I find it very relevant for the work we do. So our projects are complicated, and they can be made even more complicated if we add more processes, if our procedures are complicated. Well, it's so much more elegant to try and start from something simple and even try and make it simpler. But if you start from something simple, a simple timeline, simple processes, then you can always make them more complicated. If you start from complicated, it gets even more challenging. And it doesn't mean, it's not because something is simple that it will not achieve your objectives or it will not work. On the contrary. And so this is something I try to apply in my daily work, also with the team. And yeah, I think this is really important. And from what I see, there's loads of processes or stuff which tends to do the contrary from all of this. The other key aspect of the job is the multiple teams which are around the flight control team. So this is, for example, the flight dynamics team. They're the ones doing all the computations for orbits and maneuvers and pointing, but also all the teams revolving around all the software we use, the ground station teams, and then all the external teams which are there, for example, all the payload teams. And in the end, this is all people interacting with each other and people dealing with each other. And if the communication is good, if the people are able to deal together very well, then the project will be successful. It will really work great. And in ESA, we have a way of achieving this with all these teams, and this is called the simulations campaign, which roughly starts 6 months before the launch. And this is where we put all the teams together, and we are trained to be able to react to whatever issue or contingency would arise during the launch itself and the first few days of the mission. And this allows to bring all the teams together and to be one team composed of multiple teams. And this is really, really a key aspect of such projects. So coordination among people and people being able to deal with each other. This is absolutely key. And this is what I've witnessed in all the teams I've been coordinating with, but also directly into my proper team. So that is it from me. I hope you've enjoyed the talk, and yeah, I'm really looking forward to this ERA mission, and I think it's going to be really fascinating. I mean, just me talking about it, I just find it really, really exciting. Also, the few times, like, I'm not a scientist, I really deal with operations, and but the few times I hear the scientists talk and give their talks, it's just really, really absolutely incredible and awesome. And I see just a slight little time, we'll be reusing a lot of techniques we've done already. For example, on the Rosetta mission, we have in my division a lot of experience with deep space missions. So we're reusing, of course, a lot of concepts we already know and we know work, and we'll be adapting and tuning them for the Hera mission. On Rosetta, we did optical navigation, so using these landmarks, which allows to know exactly where the spacecraft is around the asteroid orbits. And this is key. So we know the orbit of the spacecraft around the sun very accurately, but we need to know precisely where it is. In this low gravity environment, we can roughly do whatever we want with the trajectories.
Totally agree.
Okay, I think I'm still positive in time, so it's good, but I'm done now. Thank you.
Yeah. So thank you. It was like brilliant, perfect on the timing. I think we really love this pitch, and so now it's time for you to go into the Vostok 2 room, so to engage on a Q&A session with the audience. So you can go on the Zoom link, and for the audience, just join the breakout room, and Sylvain Lodiot is going to join you for the Q&A session.
Exactly. And now it's time to welcome our next speaker. So
we'll do some disconnecting mobile.
Sorry? If please, if Sylvain, if you can actually go out of that session, you will be able to join the next one. Thank you so much. So we will continue with our next speaker. He's a robotics technologist, Jeff Delon. He's working at NASA's Jet Propulsion Laboratory, and he was actually part of the navigation team for NASA Mars helicopter